My name is Izi Stoll, and I'll be talking about qualia as an emergent property of neural computation. And things really kicked off about 30 years ago when Dave Chalmers described the hard problem of consciousness. He kind of described the easy problems of neuroscience and those that are scientifically tractable. Not that they're not technically difficult, they're just scientifically tractable. Yet he pointed out that perceptual experience is not scientifically tractable right now. When we see, we experience visual sensations. He pointed out that there's really perceptual content in every sensory modality. The felt quality of redness, the sound of a clarinet, the smell of mothballs. These perceptual contents are what we call qualia. And a lot of neuroscientists say, there's not really anything to explain. They dismiss the whole problem entirely. But I think a subset of us neuroscientists really do feel that there's something to explain here. And so I'll take my best shot. And I think the best place to start is with thinking about neural processes that are associated with qualia. And so to begin talking about this, it'll be useful to talk about a simple 3-neuron circuit, our spinal reflex circuits. When we touch a hot stove, the pain and temperature receptors in our skin are activated. And these pain and temperature receptors are connected to a sensory neuron, so that sensory neuron is activated. The sensory neuron then sends a message to an interneuron in the spinal cord, and that interneuron then sends a message to an alpha motor neuron, which signals to a muscle fiber. That muscle contracts, and we remove the hand from that hot stove. So this is a simple 3-neuron circuit, a spinal reflex circuit. There's no perception of the pain until about a second or two later when that information reaches the brain. It's only when neurons in the periaqueductal gray and thalamocortical circuits are activated that we actually have that qualitative perception of the pain. If we activate spinal reflex circuits but we don't have cortical activation, there's no perception of that signal. And so really, qualia is something that's correlated with cortical neural activity and not with spinal neural activity. So the question now is not really, what's qualia? The question now is a little more tractable. It's, what's the difference between a spinal reflex circuit and a cortical neural circuit? In spinal reflex circuits, signaling outcomes are deterministic. If upstream signals sum to a certain threshold, that neuron will fire a signal. In the cortex, signaling outcomes are non-deterministic. The probability of a neuron firing a signal cannot be predicted by summing upstream signals. Receiving upstream signals only increases the probability that that neuron will fire. So while spinal neurons are always spiking or not spiking in an on state or an off state at any given time, like binary transistors, our cortical neurons are actually calculating the probability of sending a signal. So neurons in spinal reflex circuits are deterministic. They are not sensitive to random electrical noise when gating signaling outcomes. Neurons in the cerebral cortex, however, are non-deterministic. They are highly sensitive to random electrical noise. But random electrical noise reduces energy efficiency and accuracy in classical circuits. Randomness and disorder have no meaning. So why are cortical neurons so noisy? To answer this question, we have to talk a little bit more about information and computation. The mathematical definition of information is the sum of all possible system states. It increases when there's randomness in the data, and it decreases when there are patterns or consistencies in the data. The colloquial definition of information is almost the complete opposite. It's a single meaningful state. It decreases when there's randomness in the data, and it increases when there are patterns or consistencies in the data. So I'd like to resolve these two opposing definitions of information within a single framework of thermodynamic computation. I'm proposing a natural process of generating some quantity of information, then compressing that quantity of information by extracting a signal from the noise. So we're identifying meaning in the data. So information is a thermodynamic quantity. Energy has to be expended to create information, and energy is recovered as information is compressed, as signals are extracted from the noise. And so I think this is a really important point, that when we talk about how neurons encode information, we're talking about a thermodynamic process as well as a computational process. So let's just go back to this noise one more time. It's really important to notice the difference between these contexts. So when an alpha motor neuron receives a suprathreshold stimulus, it fires. When a sensory neuron receives a suprathreshold stimulus, it fires. These cortical neurons are different. They actively balance excitatory and inhibitory inputs so that they're hovering right near action potential threshold and allowing random electrical noise to gate signaling outcomes. This is called a cortical upstate. During cortical upstates, these neurons remain suspended near action potential threshold and specifically allow random electrical noise to affect signaling outcomes. And so in cortical upstate, the stochastic charge flux significantly contributes to the likelihood of a neuron firing. Yes, there could be a suprathreshold stimulus from upstream neurons, but in general, these neurons are allowing random electrical noise to gate the action potential. So this looks like probabilistic computation. And the outcomes look probabilistic as well. Cortical neurons at an individual level have statistically random interspike intervals. Accounting for the refractory period, this is a Poisson distribution. So previous approaches to modeling these single cell firing patterns include Hopf bifurcation or Pfennefactor analysis. These are truly probabilistic models. At the systems level, percept realization is correlated with a synchronous firing of statistically random ensembles of neurons across the cortex. And again, previous approaches to modeling these population-level firing patterns include statistical methods and random projection models. We are modeling this as a random process, statistically random process. So we could actually formally account for the noise. And by modeling that noise, we can get a more mechanistic rather than statistical model to explain cortical neuron computation. So in order to do so, we have to look a little more closely at sodium ions at the neural membrane. These are ions. These sodium ions are atoms. Their position is uncertain along the x, y, and z axis. Their atomic orbital, which is related to energy and angular momentum, is also uncertain. Even time itself is uncertain. The amount of time that's passed from when the ion last interacted with the neural membrane, that's uncertain. And so we're modeling that uncertainty. We're modeling the position, orbital, and time across the x, y, z orbital and time axes, and this is a high-dimensional probability distribution. So each atom is actually turning into information. It's turning into a distribution of possible system states, and because each sodium ion can contribute to the voltage state of multiple neurons, the voltage state of each neuron is a probability distribution. It's really the sum of all component pure states, and that distribution of possible voltages is the information that the neuron's encoding. So when we look at atoms throughout the nervous system, we're talking about energy or matter converting into information. This energy is distributed across the x, y, z, time, and orbital axes to create a probability distribution, which is the total amount of information or entropy that's encoded by the system. And selecting an optimal solution to that probability distribution is both a computational process and a thermodynamic process of compressing information. So we can use 3 different mathematical toolkits to describe this process. There's a thermodynamic model using the algebra of matrices. There's a mechanical model using the calculus of Hamiltonian operators. There's a holographic model using the geometry of these wave functions. And so with a thermodynamic model, we have some distribution of possible system states for the brain, system A, and we have some distribution of possible states for the surrounding environment, system B. And within the combined system A-B, there's some consistencies, there's some correlations. And so those allow for information compression. Those redundancies allow for information compression. And so it's actually thermodynamically favored for the brain to encode the state of the surrounding environment. It saves energy to find those consistencies. And so we generate some information, some distribution of possible system states, we find those consistencies, and as the information is compressed, free energy is returned to the system, and that drives neuronal signaling outcomes because the Gibbs free energy is directly related to the neuron stem membrane potential. In the mechanical model, we're using a Hamiltonian operator, and that's really the sum of all the energy in the system. And so really all the energy that's entering the brain is distributed to entropy. And that's described by a Hamiltonian, the possible distributions of that energy and matter across the system. That's the Hamiltonian. And so we integrate all of the information, then we can take the derivative of that and identify a solution to that complex problem. We identify a possible system state. And as the Hamiltonian is resolved, the state of every ion in the system and the state of every neuron in the system is resolved. Then we can use a holographic model, and really we're modeling each probability distribution as a wave function, right? And so every atom in the system is described as this probability distribution or this wave function, and it constructively and destructively interferes with every other atom in the system. And so we'll get into that a little bit more in a moment. That's the model that I'll focus on here. But it's important to note that all three of these mathematical models show the exact same process of information generation and compression. So now we can talk about how qualia emerges naturally from this computational process. So let's go back again to these sodium ions at the neural membrane. Each one of these sodium ions is an atom, and we're modeling it as some distribution of probability amplitudes along the x, y, z time and orbital axis. And so each atom becomes information. It's a distribution of possible system states. It's a wave function. And so each of these atoms is a wave function, and it's constructively and destructively interfering with every other atom in the vicinity. And this constructive and destructive interference of wave functions is being encoded by the neural membrane. And what's important to note here is that the neural membrane is a charge-detecting polymer surface, a charge-detecting surface comprised of organic or synthetic polymers is a holographic recording surface. And so what we're getting here is information that's not only being encoded by the neural membrane, but it's actually constructive and destructive interference of wave functions being encoded by the charge-detecting polymer surface of the neural membrane, which not only encodes information, but then holographically reconstructs that information into a virtual image. And so any data being encoded by the cortical neurons in this probabilistic manner should not only be encoded in the system, but also represented like a holographic image in any modality. So it's worth talking a little bit more about the holographic interferometry, that's spelled wrong. So holographic interferometry is when a reference beam, or the previous state, interferes with the object beam or any number of object beams representing the oscillations of the matter. When this interference occurs on a holographic recording surface, it naturally generates a virtual image. And so if a reversible material like a biological membrane is used, the wavefronts are reflected in the direction of the original object. And so here, the wavefronts A and B represent the states of the object itself, or really those atoms. And the interference of these wavefronts with the reference beam, which is the previous trajectory of those ions, form a holographic virtual image. And really, this holographic interferometry was developed by Los Alamos Scientific Labs about 50 years ago, and more recently, the experimental setup for time averaging interferometry with biological films has been developed. And so we can go through the math a little bit. I know nobody likes it, but here we're modeling each ion as an electromagnetic point source. And what we can do is model the phase angle between the reference beam, the previous trajectory of each ion, and the object beam, which is all these possible trajectories in the present moment. And so the reference beam and the object beam interfere. We've modeled these as spherical waves or high-dimensional wave functions, which are interfering with each other. And so we're keeping in mind that this is a high-dimensional wave function. We're including that orbital value. And so it's important to note that when these wave functions are interfering on the holographic recording surface, the holographic recording surface itself is not a two-dimensional recording surface, as in classical holography or interferometry. We also include the z-axis because the shape of the neural network and each individual neuron has an x, y, and z-axis itself, which means we preserve that higher dimensionality when we're reconstructing that image. And so the intensity of the combined beams is proportional to the square of the combined wave functions or the square of the magnitude of the electrical field. And so then what we can do is calculate the transmittance of this high dimensional probability density or wave function. And as we reconstruct that information, we're reconstructing these electrical fields, the intensity and position of every stimulus or every aspect of the stimulus. And this causes the diffraction period pattern to be holographically projected into a virtual image with a resolution determined by the properties of the recording surface. And here we see that integration of all of those values, giving us 0th order diffraction, as well as the true image and the phase conjugate image, which combine to create that virtual image. And so we're actually getting a projection, a holographic projection of the information that's encoded by the structure. And what's really important to note here as we're looking at this image is that we are that holographic projector. We are that holographic recording surface. That's our neural network. We are the reference beam, the previous state. We are enjoying the sensory input that's coming in, that's encoded in those object beams. And as these things combine, we are enjoying that projection of the data that's being encoded. So this is a physical process of information encoding and representation. So the criteria for generating perceptual content in this framework is a truly probabilistic computation that's necessary. We need that random electrical noise to be combined with upstream signals to represent that sensory input. We also need a holographic recording surface, and the characteristics of an ideal holographic recording surface are a charge detecting membrane that's composed of organic or synthetic polymers, with even responses across the surface to ensure signal capture, a large dynamic range to provide good signal-to-noise ratio, sensitivity to low energy exposure to achieve fine signal detection, and protection from environmental factors that could impact functionality. And of course, the brain does have these characteristics. Our cortical neurons do have these characteristics. And so the constructive and destructive interference of high-dimensional wave functions on the polymer surface of the neural membrane should lead to both information encoding and representation of the qualitative aspects of the object that's being encoded in the surrounding environment. So a summary of the theory, I think it's important that we talk about information. This is the sum of all possible system states or a high-dimensional distribution of probability amplitudes. This is the mathematical and physical definition of information. So what's meaning? Then it's a solution to a computational problem, encoded by a single optimal system state to encode the surrounding environment, selected from a large probability distribution of possible system states. And so what I'm proposing is that we're undergoing a natural computation, a two-step process of generating information, then compressing it into a meaningful statement about our surrounding environment. And that process occurs naturally as consistencies are identified and signals are extracted from the noise. And so What's happening here is that the state of every ion is resolved at a single point in time, which defines the voltage state of every neuron. And that generates a multisensory percept or a predictive semantical statement about the present state of reality. And that event is correlated with a synchronous firing of neurons across the cortex. Then temporal sequences of system states are integrated together and parsed for cause-effect relationships. There's additional predictive value to be gained here. So the sequence of perceived events is a predictive syntactical statement about the cause-effect structure of reality. And it's important to note here that predictive value is a thermodynamic quantity. This is a physics paper. This is a description of how the consistencies and correlations in a combined system allow predictive value to be extracted in an energy-efficient computation. And the extraction of predictive value from some quantity of entropy releases free energy and directly affects neuronal signaling outcomes because Gibbs free energy is directly related to the Nernst membrane potential. So this is a thermodynamic computing cycle. And it's a process of information generation and compression. First, a new probabilistic state evolves over time. As each ion creates some probability distribution. We sum all of these component pure states into a probability density. That information content is both encoded and represented. We then reduce that probability density into a defined system state as information is compressed. And again, that process is paired with free energy release, which causes each neuron to either fire an action potential or return to rest. And the entire process then repeats itself over and over again iteratively. So if existing knowledge is sufficient to navigate a situation, no uncertainty, information, or conscious attention will be generated. The person will act in a reliable way, accomplishing tasks without attention. And we can imagine ourselves driving to work the same route for 10 years and maybe even forgetting to stop by the grocery store because we're just so used to that route. We just don't even generate conscious attention when driving it. So if existing knowledge is not sufficient, though, to navigate a situation, uncertainty, information, and conscious attention will be generated. That information can then be parsed for meaning or consistency. And the energy that's recovered during information compression then drives the synchronous firing of neurons across the network. And these non-deterministic signaling outcomes direct the action of the body. So really, in this framework, the perception of content, the perceptual content that emerges from the neural computation is really just a byproduct of a non-deterministic computational process. So who or what has qualia in this framework? Well, a digital circuit cannot. So there's no probabilistic coding to gate signaling outcomes. These are ones and zeros, on or off, binary transistors. There's also no holographic surface to encode and project the information. In plants, there's no probabilistic coding to gate signaling outcomes if there is a neural network at all. And importantly, plants have a cell wall covering the cell membrane. And so they don't actually have the holographic surface to encode that information in a physical manner. Our spinal reflex circuits do have the same qualities, structural qualities of our cortical neurons, but these neurons do not engage in probabilistic coding to gate signaling outcomes. They are robust to random electrical noise. There may be noise in the system, but these neurons do not respond to it. And yet, it's just the mammalian cortex or the avian pallium, which have the properties to meet this criteria. These cells engage in probabilistic coding, have statistically random outcomes, and they have the properties of a holographic recording surface. So these criteria are met. There are additional criteria which include sensory input, motor output, and a non-equilibrium thermodynamic system which traps heat to drive computational work. So that's the summary of this approach. I gave it my best shot. I don't know if this explains everything, but I'm very, very happy to engage further. Thank you so much to everybody who gave me feedback after this talk and allowed me to clarify some of the key concepts. Thank you.